which is now the applications portion of the Laplace transform. So the idea here is that the Laplace transform can be used to, when you have a derivative, whether it's first order, second order, and so on. The idea here is that these are going to be good for IVPs and specifically for linear differential equations with constant coefficients. So now, here's why, or how it's going to work. So let's say we have a run-of-the-mill nth order differential equation. So nth order, and we also have some initial conditions. Y of 0 is y naught. Y prime of 0 is y, we'll call it y naught prime, and so on. All the way down to the nth derivative initially equaling, let's call it y naught to the n minus 1.
Attention students, just a brief reminder that tomorrow, Thursday, there will be a late start, but there will be no seminar for freshmen as noted in your planners. Again, there will be no seminar tomorrow, just a regular late start. Have a good day.
Okay, so now what we're going to do is apply the Laplace transform to the whole differential equation. So then what we're going to get is something that looks like this. Lead coefficient, and then we take the Laplace transform of the nth order derivative. And we do that for every derivative, or y, that we see. Okay, we kind of know from yesterday what's going to happen anyway. If I go ahead and compute the Laplace transform of a derivative, actually it's not from yesterday, a couple days ago, let's leave the lead coefficient out. And now this portion here is going to become s to the n y of s minus s to the n minus 1. And now we start to work our way up from y of 0 up to y prime of 0 and so on. all the way down to the n minus first derivative and we're not going to do this for every term, but we'll do it for a couple. Again, applying the Laplace transform definition for derivatives. Okay, there we're going to get lead coefficient a sub n minus 1. And now here we start with the highest power of s, which would be s to the n minus 1, y of s. And we do the same thing. We decrease the power of s and work our way up from y of 0 up to y prime, and so on. Now this will be the n minus 2.
Attention students, just a reminder that tomorrow, Thursday, will be a regular late start. As noted in the student planner, there will not be a freshman seminar tomorrow. It will be a normal late start, and there will be no seminar for any students. Have a good day.
And we'll go all the way down to a naught. And the Laplace transform of y will be capital Y of s. And then that's going to equal the Laplace transform of little g of t, so we'll call that capital G of s. So now what this allows us to do, as we take the Laplace transform of every derivative, the nth, n minus first, and so on, every term is going to have y of s. Okay, so what we're going to do is factor out capital Y of s, which would leave us with something like a sub n s to the n from these this coefficient here, plus a sub n minus 1 s to the n minus 1. That's this coefficient here. And we go all the way down, repeating, taking out a y sub s until we take out a naught. And then what we can do is get all the other stuff, so everything that doesn't have a y sub s, over to the other side, which I'm not going to write out, but everything else. We'll do it that way. Okay, so you're going to have a whole bunch of terms, including g of s and including the addition or subtraction of anything that we needed to get rid of to get y of s factored out. And then what this allows us to do then is now you can solve for y of s and then apply, so this is like the second step, the inverse transform. Okay? Y of t is just going to be the inverse transform of y of s. And there is your solution. Okay? So, I mean, the actual procedure isn't too bad. Once we go through it once or twice, you take the Laplace transform of everything, Laplace everything, and so to speak, factor out y of s, which is going to help us figure out what y of t is. Once you factor out y of s, you can apply the inverse transform and then any other theorems that we need to along the way. Okay. Questions so far? All right. So let's look at a run-of-the-mill first order equation, dy dt minus 3y equals e to the 2t. And Initial condition is 1. Just to make sure that we still remember, if we didn't just talk about what we talked about, what would we do here? What's that? You could use an integrating factor. What else? What about this guy here? Annihilate? I mean, there's a lot of options, right? Okay, so the one nice thing about Laplace transforms is that because of the way we derived how to apply these guys, at the end of the problem, you don't even have to worry about the initial condition. It'll get plugged in as we work through it. Okay, so let's go ahead and, if we take the Laplace transform of the entire equation, we get something like this. Okay, now the Laplace transform of first order derivative is what? Good. Minus 3, and then this will just be capital Y of S, equal to, what's the Laplace transform of e to the 2t? One over S minus 2. Okay, good. And now we do exactly what we said we were going to do. Factor out Y of S. And then what's left? If I factor out Y of S, we're just going to get S minus 3, right? On the other side, we're going to get 1 over S minus 2 plus our initial condition Y of 0, which is 1. Okay. So then now we just figure out what Y of S is going to look like, so divide by S minus 3. Actually, maybe why don't we combine the fraction first? That might make things a little easier. So this would be the same as 1 over S minus 2 plus S minus 2 over S minus 2. I still have S minus 3 here, sorry. So I'm going to get S minus 1, S minus 2, and then if I divide by S minus 3, I have that the transform of this differential equation looks like this. So after we divide by S minus 3, here's where we're at. And now all we have to do is what? Take the inverse of both sides. So then this will give us Y of t. And now how should I find the inverse of this one here? Partial fractions. Okay, so let's do that real quick. s minus 1 over s minus 2 times s minus 3 will be decomposed into a over s minus 2 plus b over s minus 3. So s minus 1 will equal a times s minus 3 plus b times s minus 2. So a plus b has to equal 1. Negative 3a minus 2b has to equal negative 1. And if we solve, let's see, maybe double this equation, add them up, you get negative a equals 1, so a is negative 1. So that means b would have to be 2. So then what we're doing is taking the inverse transform of negative 1 over s minus 2 plus 2 over s minus 3. And once we do that, we're done. What's the inverse transform of negative 1 over s minus 2? Plus, there's our solution. Okay, so we're given an initial condition. We kind of work it in at the beginning, so now we don't even have to worry about it. Once we get to y of t, we're done.
Does this have to do the Laplace transform, or are there other transforms out there that will do the same thing?
Depending on what kinds of functions we have over here. There are Fourier transforms, and like you can do series things with this. Like if you have periodic functions, that's something that I want to eventually get to if we have some time. But I mean, yeah, this is not the only transform out there that'll help you solve the equation. But for us right now, since we've only talked about linear equations with constant coefficients, this is a pretty good technique. Okay. All right, why don't you guys try this one